Okay, so let's try this again. We are starting where we left off. And so when we last met, we're talking about the activation energy barrier. And the activation energy barrier is a minimum requirement that must be met before something happens. Now, the context here is the chemical reaction, right? So you can see here in this picture that the left side is separated from the right side. Let me hold on a second. Let me just scroll down so I can get the most latest message. You have the reactants energy on the left side and the energy of the product on the right side. So the idea is, in order for reactants to become products, the reactant energy must fulfill this minimum requirement here, and that minimum requirement is the activation energy. Once the activation energy, that minimum requirement standard is met, then the assumption is that products can be made. So one of the learning goals in this class is knowing how to interpret a graph. What is the graph communicating to you? Of course, the context of conversation matters, right? Here we're looking and seeing that when you're comparing the two sides, in the beginning of the reaction, let's look at the graph. Now the graph is supposed to have a title. I'm assuming this is the title here. This is not really the title, that's just like the label of what this part is. But it's supposed to be an energy versus reaction progress graph. And so the y-axis is showing us the energy of the reaction. And then of course here, the energy is increasing from bottom to top. So if anything coincides or matches or is placed in the bottom, it has a lower energy. So you can see here, products have got lower energy, right? And then the reactants that mark the beginning of the reaction, these have higher energy. And then, of course, the x-axis right here shows us the progress of the reaction. In other words, this is telling us that when you start from left to right, you're going from the beginning. So right here, BEG for the beginning, for an END for the end. Yes, it's exothermic because the beginning of the reaction starts with a higher energy, and then when the reaction is over, it's a lower energy. That means that somewhere in the process, energy got lost, right? Yes, it is. It's okay. But at least that means you were processing the information, right? Very good. I mean, it's okay if you are ahead of the PowerPoint. That just means you are connecting with the information, and that on the all the PowerPoint is doing is confirming your observations, right? Yes, the reaction is exothermic. During the reaction, heat is being lost, right? That's why it ends up at a lower energy level. Very good. So you want to be able to interpret exothermic reaction being given this energy profile diagram, or endothermic, right? And then of course you have your activation energy barrier. Very good. So we're told here the activation energy, once again, is the amount of energy needed to convert reactants into the activated complex. Now, I have to define what the activated complex is. So as we are in general chemistry, once the reactants are up here, they're given two possible names. They're given the name activated complex, or they're called transition state. Same chemical. Oh, let me see. I'm out of room here. Transition state. What does this mean? It's called the activated complex of transition state because it tends to have higher energy than even where you started, right? In order for these reactants to be able to form products, they had to absorb a lot of energy, get to this higher level, and right before they form products, they are in that activated complex state for a fraction of time. Okay? And while they're there, we're defining what they're called and their characteristics. So they're called transition state or activated complex. They tend to have the highest energy possible. So we're told here to give us more information about what the chemicals look like when they're in that heightened energy state. We're told the transition state is a chemical species with partially broken and partially formed bonds. So it's kind of like a snapshot. Okay, imagine that. Okay, this is me going into uh, makeup mode. Imagine, you know what? Let me not do makeup. Let me pick something that's more relatable to everybody. Imagine you're building a house and you're doing a remodel or, yeah, some kind of building of a house, right? The beginning is where you're starting. The middle is when things look super chaotic. So when somebody walks into the middle of your project, it is chaotic. There's a lot of noise, there's a lot of construction, a lot of dust and dirt, and things are everywhere. So there's a lot of movement though. So you can tell something is happening. So you can equate that middle state where everything is a mess to be the activated complex. But that middle state, even though it looks very disorganized, it does have high energy and it's necessary in order to get to your final product. So the activated complex tend to show you things partially done, right? And this is how I remember this when I was in school, because remember, this is you guys' time. Back in my days, we didn't really even have PowerPoint, y'all. This is like way, way back. Teachers are teaching old school. They use a chart. Yes, the reaction is over when everything settles down. So think about HGTV. During that last moment, right before the reveal, they're sweeping the last dirt and then putting the carpet and everything well, throwing the throw pillows in the chair. And right before the reaction is over, everything is settled and everything is calm and the reaction is over. Okay? So in the heightened state, transition state, you have partially broken bonds and partially formed bonds. So you're right in the middle of everything. And that part is very important. Now, in this class here, we introduce the concept of partially broken bonds and partially formed bonds. For chemical reaction to take place, bonds must break and bonds must form. So in the instant, that snapshot where you get a picture where bonds are breaking and bonds are forming, you are essentially at transition state, and that tends to be the state that has the highest energy. Okay, we're told always very high in energy because it has partial bonds. So there's so much chaos. One time I was trying to tell my friend, I was trying to complain to her about how chaotic my life felt. Now, she is a high school teacher who's taught chemistry, physics, and biology. So when I communicate to her, it's at a whole different level. And I'm on the phone telling her, I feel like my life is in transition state. You know what I mean? It is so chaotic, and there's just all this stuff happening, all this bonds breaking and bonds forming. And I feel like I'm at a very, very high energy. She's like, there, I understand what you're saying. It's a whole different level of a conversation. Then later on, of course, things calm down, right? So you don't do that with your regular friends, the ones who get it. Okay, so here we're seeing what we are learning, but this is actually an organic question right here. And this is showing us what we just learned, which is you have a chemical reaction, you have the starting point, you have, now they call this the products. I don't like that, but I understand why they're saying this, because there is more to this reactant than what we are seeing. The reaction actually starts further left. What we are seeing is a snapshot of maybe the second part of the reaction. So that means that these products were made by a different reaction. Then starting from here, we're making new products. Okay, so this is for our reference, this is our reactant, this is our starting point. You can see you have OH minus, and it's doing something with CH3Cl, and this is our starting point. And then when we look at our ending point here, now we have the CH3 with the OH instead of the Cl, and now the Cl is by itself, right? So somewhere somebody got replaced. And this reaction in organic chemistry is called the substitution reaction. So you can see where the substitution took place, right? Pretty logical. Somehow the OH replaced the Cl. Now it's not called replacement reaction, it's called substitution reaction. Okay, that's the term they use to name this reaction here. So at some point, OH replaces Cl. You can see that from the starting point to the ending point. But in the middle, when the replacement is happening, it almost looks like a weird relay race, right? In this case here, what I would say to describe a transition state, Cl minus bond breaks. You can see that, right? Because Cl is going to be leaving. while OH bond forms, but it's not fully formed. It's happening at the same time. So when you get to organic chemistry, you will learn what this is called. But transition state shows you both bond breaking and bond forming. And because this is transition state, the other way you illustrate that is by using brackets and this little symbol right here, the hashtag, right? This is not like the hashtag is here in context is this is a transition state where we are showing what bond is breaking, what bond is forming. And so while the Cl is leaving, the OH is coming in. Okay. In this reaction, the Cl doesn't leave first and then the OH comes in later. No. This relationship is breaking while this relationship is forming. It's like carbon couldn't even wait for Cl to leave, pack up its bag and leave before it started forming a relationship with OH. It just happens at the same time. Okay, and that's very important in the mechanism. So we won't go into organic, we'll stick with 1412. Okay, as we're talking about this, we can see here that starting materials have a certain energy. So let's see. We don't know exactly what the energy is. All we see is the gap, right? So the reactants have to gain 102.6 kilojoules per mole of energy to be able to get to the transition state right here. When they get here, the transition state form, which is called transition state, or the activated complex has to lose all the energy it gained, right, to get to here, and lose even more to get to the product. So when they're showing you the negative here, you kind of have to understand the signs, and it's sometimes it's difficult to communicate things even in the picture. The negative they're showing you here is what is happening when the transition state or the activated complex is going to the product form. It has to lose all the energy it has to be at this new position. So it loses the energy that is due to this gap right here. So it loses 102.6 kilojoules per mole, right? Then it has to lose this amount again, 100.5 kilojoules per mole to be at the level that the products are in, okay? Now, lower energy is synonymous with stability. So you can see the reactants here were not as stable, the products are more stable, so these are stable products. Once again, this reaction is exothermic, okay? So you want to remember all that. Okay, so here we're learning this. We talked about this in 14. Actually, no, this is the first time we're talking about it. No, we'll talk about it now, then we'll talk about it later on. Okay, there's something called kinetically favored reaction versus thermodynamically favored. You have to learn this now because for those of you going into organic chemistry, you will need to know one versus the other because you will be asked to devise, to come up with a reaction mechanism. So you will be writing a step-by-step procedure to get a certain kind of product. They will ask you sometimes, give us the kinetically favored answer. You need to know what kinetically favored is. Or they will tell you, give us the thermodynamically favored answer. You need to know what it is to know what path to select, okay? So what is kinetically favored? Kinetic has to do with this chapter here, rate. It has to do with speed. So you want the reaction that can happen faster, okay? So what I'm going to do here, since I didn't draw this picture, it's hard for me to modify it. I thought I had a page down here. I'm going to draw my own, add a page here, so I can show you what kinetically favored looks like. Okay, I always think about kinetically favored to be a reaction that takes place fast. So let me try to pick the color because one semester I switched the color. I was just going with the color I preferred and it ended up being opposite with the color here and then somebody got confused. So let's see. Here the blue is kinetically favored. Yeah, the blue. So let me stick with the blue being kinetically favored. The labeling they chose here is opposite too, so it makes it confusing, right? But here's the idea. So the blue path is kinetically favored because it doesn't have to do with the color as it has to do with the activation energy barrier. So the barrier is small. Oops, hold on. This is a challenge to draw here. Okay, this is kinetically favored exothermic reaction. Okay, now by looking at a reaction by itself, you can't tell it's kinetically favored because to say something is fast, you have to compare it with something else, right? That's slower, so you can judge and say this is faster. So remember, this has to do with energy and then profile of the reaction. So yeah, and this is kinetically favored. Now I'm going to draw the thermodynamically favored version of this reaction. In thermodynamically favored reaction, this is it right here. So this is thermodynamically, ooh, I almost didn't get that word out, favored. No, I'm revolting. I'm going back to my old way of spelling stuff, the word favored. Thermodynamically favored exothermic, right? Reaction. I'm keeping it simple by looking at exothermic reaction in both cases, right? They're both exothermic because the starting point is higher than the ending point. This second one is thermodynamically favored. So what is the biggest difference between these two? Okay, we haven't gotten to that chapter yet, but thermodynamic has to do with stability. Stability. Okay, so when you're saying thermodynamically favored, you're trying to say it's going to make a more stable product. When you're saying kinetically favored, it's going to make the product quickly. So yeah, thermodynamically favored product is the one that is making a more stable product. So when you look at this here, remember in chemistry, in a way. So here's yeah, it has to do with speed, right? So thermodynamic doesn't mean it's not moving. It is moving, but it's not moving as fast. So when I was learning this, for me to make sense, because as a student, these words meant nothing to me, right? So I had to tie it to, once again, my life. I was that kind of selfish learner. So I said, oh, if I was to get a life lesson from this graph, it would be like, okay, what was it called? Slow but steady wins the race. Something like that, one of those saying that will apply to this. In other words, some things in life that are worth it. And for this, oh, interesting. Some things in life that are worth it are worth waiting for. Okay. And worth it here will have to do with stability. If your goal is a stable product, then you want to go the thermodynamic way because that will give you stability. It will cost you time, but you will get a more stable product. Okay, so from here you can argue, yeah, good things are worth waiting for. They take a lot of energy. You have to put a lot of work into it. You have to overcome the higher activation energy barrier. But in the end, it's worth it because you get a more stable product versus quickly gained. Oh, I don't know how to say that phrase. If you gain stuff very quickly, yeah, you get a decent product, but it's not as good as the one that you got from waiting, right? This is kind of like quickly gained products. It's not as challenging. It appears to be easy in the beginning, there's less barrier to overcome, but in the end, what you're getting is not as good as what you could have gotten. And so for me, can you imagine? Just understanding those words was not enough for me, but tying it to some kind of life goal, I was like, oh, okay. So I'm able to recreate this because it's not just a graph. No, it's communicating a life goal, right? I know there's a phrase that goes with this. I've just forgotten what it was. I've forgotten exactly how to say it, but yeah. So yes, since organic chemistry is one of those chemistries that you learn to learn how to synthesize drugs and synthesize compounds and stuff, it's important as a scientist to have that skill set to know when it's necessary for you to get a kinetically favored product and when it's necessary to get thermodynamics. And the experimental conditions required to get one or the other are not the same. So you have to know either experimental design, right? The teacher used to trick us with these things. He'd be like, okay, I want you guys to get this product this way in this condition. And then you have to go back to 1412, remember all the stuff, maybe expose the chemical to sunlight, filter it, do this, do that. Oh my goodness. It was hectic, but it was also fun, right? So that's why we learned that here. Now the reaction mechanism. So the chemical reactions are generally described with an equation listing all the reactant molecules and the product molecules. But we're being told there's more to the story than what we see. Most reactants occur in series of small reactions involving one, two, or at most three molecules colliding with each other. So they're not saying that here, but it's implied that when we're talking about reaction mechanism, since we're looking at the play by play, we're trying to see what molecules are bumping into each other in the scene that we are examining. Okay? Describing the series of reactions that occurs to produce the overall observed reaction is called reaction mechanism. Okay, so I think of it like if this is a movie that you're watching, and if it's a romantic movie, right? So I'm going to what you were saying, a love story. The scene that we're looking at, does it involve two characters? Does it involve one character going through self-discovery? Or does it involve three characters? So here we can have one character, two characters, or at most three characters. And now characters, of course, being molecules. And of course, in the end, we are learning about reaction mechanism because knowing the rate law of the reaction helps us to understand the sequence of reactions in the mechanism. And we're going to be doing that. So an example. And as we're looking at this part right here, remember, we're looking at the overall, right? This right here is the overall mechanism. This is like the bottom line. If somebody were to ask you, what are you doing right now? You're watching a movie. Oh, I'm watching a romantic movie. Like I was recently tired. I'd been working all day long. I needed a break. So I was watching a romantic movie. And my friend from work asked me, so how is it? I'm like, you know how it is. Boy meets girl, they fight, they get together, it ends. So the synopsis I provided her was pretty much the overall reaction. And she's like, how was it? I was like, it was okay. Now I told her, well, they did have an interesting twist, an interesting plot within the movie. So as I started to get into the plot and the little twist, that would be the reaction mechanism. What distinguishes one romance movie from the other as you're going to the plot and the twist. And then this character came out of nowhere, and then he got into the plot, then he got taken out, they shot him or something like that. All that play by play is your mechanism. So when you're given the bottom line, that's the overall reaction. So our overall reaction shows us that H2 reacts with 2ICl to form 2HCl and I2. But the reaction mechanism actually shows us that this is happening via two steps. Yes, yes. So it's like somebody giving you an oversimplified version of what happens. So up until this point, chemical reactions have been exactly that, the cliche or the oversimplified form of what's actually happening. Now we're looking at the play-by-play, what is really happening in the beaker, in the container where the molecules are reacting. So the overall reaction, this one here, takes place in two steps, okay? So over here, it looks like the hydrogen, the one hydrogen particle is reacting with two of the ICLs, right? But in the mechanism, the one hydrogen particle technically reacts with only one of the ICL. And then it produces HCl and HI in the first step. Once the HCl and the HI is formed, the HI goes ahead and reacts with the second ICl particle, and then that produces even more HCl and I2. So what we don't see in the overall reaction is this part. We don't see HI at all in the overall reaction. Yet HI is a very important part in the second step. Without HI being formed, the second step will not happen because HI is an important reactant in the second step. Okay, so here I usually say when I'm learning this, as I was relating it to my life or any life outside of the lab or lecture room, I'm thinking this is when they bring that one character. If it's a long TV series, they bring the character in and he's gonna die. When I was watching Star Trek, when they brought a new character, I'm like, oh, I'm like, wait, don't fall for them, don't like them, they're gonna be killed, and then bam, they got killed. And I was like, why you gotta do this to me? Why? That's the intermediate right here. They brought them just to kill them, right? So they show up here, they get made. So the intermediate is produced first, right? So out of nowhere, they're brought in, and then they're used. Intermediate is consumed. Right, just like that. They were there, then they weren't. Then the reaction is over. But it's important to know that guest appearance character is important for the story, right? Without them, the story will not move along because they're an important integral part. They're just not going to be there in the beginning of the series or the end, but they will show up in the middle just to be killed off. Or somebody breaks up with somebody, so they're not important anymore. Okay? So as we're looking at the reaction mechanism, each of those steps in the reaction mechanism. Oh, thank you. You can see I watch a lot of movies. I can't remember the names, who the actors were, but I just know the gist of it, so I can remember it here in chemistry. My husband's like, who was the actor? You know that one guy that was in the other movie? He's like, no. I'm like, there's too many of them. So yeah, each of the reactions in the mechanism is called an elementary step. So remember, the many steps are the parts that communicate the whole, right? Yeah. So just like we did in 1411, we did Hess's law, and Hess's law had those series of reactions that kind of give you the overall. We're seeing that ideology, that way of looking at reactions here again. Okay, so the series add up to give us the whole. Same idea, different context. Okay, so they're showing you here, how do you get the whole from the parts? This is the overall reaction. Once again, these two are the ones, the elementary steps from the mechanism, right? So they're showing you here that if you add the two elementary steps, you end up with the whole overall reaction, right? And then you want to examine your reactant and see before you add reaction, like we did in 1411 with the Hess's law. You examine to see, do you have the same chemical formula with the same physical state appearing on both sides? Even if the coefficient is different, you want to go ahead and deal with that. In this case, we have the exact same formula here and here, cancel it out. And then the ones that do not cancel out, you want to go ahead and add them, consolidate. So here we end up with H2 down here. This is ICl, ICl. This is the same chemical, same physical state. Just add them. We end up with 2 ICl gas. This is the gas right here. Plus, we have double the amount of HCl. Oops, no, this is not plus. This is to give. Yields, right? 2 HCl gas plus I2. Right, which is pretty much the overall reaction. So the elementary steps get added to produce the overall reaction. But don't forget, HI had a very important role. HI is the intermediate. Okay. The intermediate, I want to see. In Hess's law, we didn't use the terminology, but we canceled off the reactant and the part nonetheless, but you want to be able to identify the intermediates, right? Okay, now we're defining more terms, and this is molecularity. So remember when I was telling you when we were examining the scene, go back to the whole movie analogy, the scene that we're looking at. In that scene that we are examining, is there an important interaction between maybe just one person doing a self-examination, two people doing something together, or three people? Molecularity here has us examining how many particles are involved in the step you're looking at. So if you have a unimolecular step, that usually involves just one particle, and the chemical reaction will illustrate that. If you have a bimolecular step, it involves two particles, and of course you have termolecular involves three particles. So we're told naturally the maximum is three particles, where the elementary step that we are examining involves the collision of three particles. When they say here, what is it involving? We're talking about collisions, or maybe one particle breaking apart. Okay, it's hard for one particle to collide with itself, but the one particle may fall apart, decompose, something like that. Here we have two particles colliding together. Here we have three particles colliding together. Since it's hard to have three particles collide together, this tends to be extremely rare. What we are saying here is if you have a chemical reaction that it has a prerequisite of three specific particles colliding together. Yeah, oh girl, stop. Yes, like that. Like making us triplets. How rare is that, right? Yes, it is so rare. So in that case, it does happen, but it's not very common, right? Okay, yes. Thank you for adding to this energy right here. I can only bring so much energy, right? But of course, when somebody else brings more energy, we get even more energy. Okay, so you can see here. Now, the type of reactants doesn't really matter. It's the number that matters here. So you see this first example here? These are all elementary steps. And so when we're dealing with molecularity, we only use that term when we are examining the scenes, right, in the big picture. So when we're looking at the elementary steps, we don't use the term molecularity when we're looking at the overall reaction, because we know that overall reaction is an oversimplified version of what is really going on, okay? So when you have only one reactant forming products, like a decomposition reaction, that's just one molecularity. Here you have two of the same reactant, two molecules required to form a product. So this can be written as 2A to form a product. That is the molecularity of 2 because it does require two reactants to collide with each other. Here you have two of the same, two but different reactants. It is still bimolecular. So this is oh, did I write the term here? The first one is also called unimolecular. And then the second one is called, right here, unimolecular, then bimolecular, then of course termolecular. It was mentioned back here, right? Yeah, uni, bi, ter versus tri. I don't know. So yeah, with the two, oh sorry, did I just say ter? I just kind of went. This is ter, ter, ter. These two are bi, right? With a bimolecular, you can have both molecules being the same or different. Here we have three cases of ter showing you all the molecules being the same, two being the same, one is different. Here all three are different. They're just different variations of the ter molecular. Oh yeah, sorry, that was a typo. I just kind of go off when yeah. Exactly. So here is the other thing. So it will appear as though I'm saying something and I'm contradicting myself in what I'm about to say, okay? From the elementary steps, from here, knowing the molecularity, you can write the rate law directly. So these are, right here, rate law equations from, I shouldn't just say from, it's not just from, it's directly from, yeah, elementary step equations. Okay, so here's the deal. Okay, so the rate law helps us to predict how each reactant's change will influence the rate of the reaction. So for that one, I can't use the movie scene because the movie scene doesn't really work. For that one, I have to use a relay race scenario. Okay. In a relay race, you have many players, usually four, that are supposed to all run. All four have to run to complete the race. And each player or each runner can help the group win, right? So some people run very fast, some people don't run very fast. But here in the rate law equation, this is a generic form. You have your first reactant, which is like your runner, and then you have the order of reaction n, which is telling you how increasing the amount of the reactant will influence the rate. And this is the order that tells you how that reactant influences the rate. And then you have the second reactant. And the second reactant's concentration may influence the rate differently. So you have a different order for that. That's how I view it. I view it like a relay race because I always try to figure out what parts of my life tie into the concept I'm discussing in chemistry. And this is the best I've found so far. If you think of something different, feel free to share because I'm always ready to upgrade the analogy, right? But not necessary. Not necessary. In this case here, you have NM. Now, N and M here stands for it can stand for first order, it can stand for second order. So the higher the order, the greater the influence on the rate. So you can say a really, really good runner will get a higher order. An average runner will get an order of one. A runner who shows up but does nothing to the race gets an order of 0. And then the one who slows down everybody else gets an order of, let's say, -1. So this is like a whole different analogy just to describe the order of reaction. Okay, so hopefully, so you kind of want to separate this, the rate of reaction rate law from the reaction mechanism, because that's kind of two different things. Okay, so with this one here, think relay race, where each runner has their ability and the scientist or the coach is trying to figure out the ability, and he places them at different positions based on the ability. Some people run really fast and help the race, they will have the highest order. Some are intermediate, they will have an intermediary order. And then those who don't really run fast or that slow will have a 0 order. The ones who run really, really slow, below expectation, and kind of slow everybody else, or maybe they even fall, so it's even worse, or drop the baton, you give them a negative, right? So if you watch the other videos before this one here, it will make more sense in context of that explanation. So real quick over here, you can see in this first scenario here, this A, the way the reactant A behaves is first order. So compared to this second case here, this is second order. So this reactant influences the reaction rate more than the first one does. Right. If they drop the baton, that slows everybody down. Doesn't matter how fast the next person was running, it slows everybody down. And when that happens, essentially that individual runner, regardless of what everybody else did, slow the reaction down. Right? So yeah, so that's what these orders kind of tell you. They tell you how these reactants influence the overall rate. Right? So yeah, over here we have second order. For these two different reactants, A and B, each one is first order. So even though they are two different reactants, two different people, they have the same level of influence on the rate of the reaction. Each of them is first order. Here you have one reactant being third order. So this one reactant by itself influences the rate by quite a bit, more than the second order, more than the first order. Here we have two reactants, right? The A influences the rate of the reaction more than B because A is second order and B is just first order. Okay. Here we have three different reactants, A, B, and C. All of them influence the rate the same. But what I wanted to focus on here is the fact that I mentioned before, when you have a regular reaction, you really cannot write the rate law for an overall reaction directly. So while I'm here, I want to restate that. This was stated before. You can't write a rate law directly from an overall, overall reaction. So after making that statement, why am I now writing a rate law directly from elementary steps? While you can't write the rate law directly from an overall reaction, you can write a rate law equation directly from an elementary step. Because remember, in the elementary step, all the important details are being discussed. In the overall reaction, since you're getting an overview of what's going on, the important details are not being discussed. So to write a rate law from there will be missing out on the important details. That's kind of how I rationalized this when I was a student, because I told you guys my memory is not very good. So if something made sense, then I could remember it more than just memorizing facts, right? So I was like, okay, I can see the overall is an oversimplification. So if you write a rate law from there, you're missing the important step, such as the intermediate. It was important for Bob to break up with Brittany so that Brittany can fall in love with Chase. I'm just making up names. Yeah. If she hadn't been hurt so bad by him, she wouldn't have realized how good Chase was this whole time. Kind of like that. And so it's important for us to know the intermediate's role in what's going on. Okay. Yeah. So as we look at this here, the rate law is written following that format: rate equal reactant raised to the power of the order. So here, once again, I know it's different from what I said before, and I'll summarize it so we can make sure we can reconcile this to everything else. The rate is written in this format. Rate is equal to K times the reactant, whatever it is, raised to the power of the order. But the order here also goes with coefficients. So as you're working on your homework, please don't try your homework before reading this stuff, because completing the homework is meaningless. K is the rate constant. Yeah, it's the rate. That's just how they write the reaction. K is a rate constant, right? So you want to go back and review, because we talk about the rate constant, the units, but when you go back and review the all the stuff before this, you see how it kind of works out. It's the rate constant that appears in all rate law equations, and sometimes in the absence of the rate itself, the constant represents the rate, because you can see from their positions here, they're directly proportional, right? So the lesson I did before today, I was talking about where the rate constant was used in a different context to relate temperature and how you can use temperature to make a reaction go fast. In that case, the temperature was affecting K, not rate, but since they are directly proportional, if T affects K, T also affects rate. Weird stuff that chemists do, right? But it's all that mathematical relationship stuff that they're doing here. So for this part here, you write the word rate. Where it says reactants, put the reactant they have here. So I'm going to erase it so we can, oops, that's not the eraser. This is the eraser. I'm going to erase it so we can see how this works out, because this part is important. Okay. So for all of these, the word rate is there. Rate. For the first one, A is the reactant, so it's put here. Do you see the coefficient? This is just 1, right? So the order is placed here as 1, and the 1 matches the coefficient, order or coefficient, because it's only 1A. Here, if you consolidate this, you get 2A equal product. So when they wrote the rate law, it's rate equal K is always there, A is the formula for the reactant, and then the coefficient becomes the superscript here and the order of the reaction. Okay? So since it takes twice the amount of A for this step, that means A influences the reaction rate even more. Okay? Over here we have A and B, each one influencing the reaction. So you have the rate, the coefficient on A is 1, B is 1, so it's rate equal K, and then concentration of A raised to the power 1, concentration of B raised to the power 1. So the ones are implied, so they're left. Right. The ones are implied, so they're left out. Here we have 3 times the A. So it's kind of like rewriting this equation as 3A to give you products. For that reason, you have rate equal K, A power 3. Okay, so it's important to see it this way because they will ask you questions like this. Given this elementary, and the key term you're looking for there is elementary step. Given this elementary step, what's the order of reaction? You either be given an equation like this or a rate law like this. Remember, the order of the reaction is the exponential number or the coefficient in the elementary step. So you want to know this interchangeably back and forth. Okay, now that we know that, we're going to be practicing our own rate law writing. So we're going to be writing rate law for elementary steps. Remember, you can only write rate law for elementary steps, not overall. You cannot write a rate law for overall reaction, right? But you could do it for elementary step. So we're told each step in the mechanism is like its own little reaction with its own activation energy and its own rate law. So the rate law for the overall reaction must be determined experimentally. So we're going back to stating this. We weren't lying there. For the overall reaction, you must determine the rate experimentally. But for the elementary step, you can write the rate law based on what you have in the reactants. Okay? So let me write this on a separate page so you can see how I'm writing it out. Because sometimes, I don't know about you guys' mind, for my mind, if I'm looking at something where the answer is there, I confuse familiarity or understanding the progress with really understanding what's going on, which is not the same thing. Okay, so even though it's literally written up here, I'm going to write it again. These are my 2 elementary steps, right? Steps. So apparently it takes 2 steps to get to the overall reaction. This is my overall. Okay, so for step 1, I'm going to call this rate 1 because this is my first step, okay? I put K right here. And then I have my 2 reactants here. So I'm going to write here in parentheses, my first reactant is H2. I'm writing it for this one here. And then the coefficient here is 1, so raised to the power 1. The 1 is implied. Second one is ICl raised to the power 1. The 1 is implied. Okay, the coefficients of both these reactants are 1, so that's my rate law for my first elementary step. Okay, so this right here is the rate law. When they ask you for the rate law, what they're asking for is an equation for the reaction. Okay, and then for my second elementary step, I write it in the same format, rate 2. Also K is the rate constant. And then here, this is HI for the first one. There's no coefficient here, so the 1 is implied. And over here, I have ICL, and this is the second one. Also, coefficient is 1. So now I have to, now they put K1 here, K2 here. Yeah. So we got that, right? I have my rate laws for my elementary steps. Now, do I have my overall rate law? Not necessary. I need more information to be able to figure out what my overall rate law is. Plus, they said here, the overall rate law must be determined experimentally. Okay? So now that we have this here, I'm going to go ahead and move on to this. Now, we're told that, before I get into the next thing here, let me mention this. We can determine the overall rate law from the rate law of the elementary steps. We just need one more thing though. We need to know the slowest step. That's right, you heard me. We need to know the slowest step. The slowest step is the rate determining step. So as I write this, I'm just like, this is so sad. It is so sad, but sometimes it's real. If you've ever been in a relay race, sometimes the slowest person can drag the whole team down, right? Sadly, in the chemical reactions, this is the reality of the chemical reaction. It doesn't matter how fast the fastest step is, the overall rate of the reaction, yes, is determined by the slowest person. I don't know about y'all, but this hits me deep in my heart. The slowest person slows everybody down. That's what they're saying here. The slowest step slash person is the rate determining step. What about the fast person though? No, the slowest step is the rate determining step. Okay, so we can figure out the overall rate of the reaction by knowing which of the elementary steps is the slowest. And when we know that this will determine the rate of the reaction. Remember, we are studying all of this so we can manipulate the reaction. In other words, the deep message that's been communicated by all we're learning here is if you want to make the reaction, work on the slowest person. If you want to make the reaction go fast, spend time on the slowest person or the slowest step. Make that step faster because the rate law, which essentially the rate determining step is the rate law of the slowest reaction and therefore the rate law of the overall reaction. Okay, so you want to make sure the slowest person is moving faster and that affects the whole reaction. So here is a problem we get to investigate. We're told another reaction mechanism to investigate. Okay, we shall investigate. This is our overall reaction here. NO2CO, NOCO2. Okay, so we have our reactants and we're told that. So as I'm looking at this, I'm going to judge this as my overall because it appears by itself. And then when it says mechanism, this is of course the mechanism of this step by step, right? Okay. So I have a rate law of the overall right here. They're telling us the rate law of the overall is K times only this reactant. So you see how you can't really write the rate law of the overall directly from here. Had you tried to do that, you would have said rate is equal to K NO2 times CO. But in reality, this is the rate law here. So you can't write the rate law of the overall from the overall reaction. You have to get it from the reaction mechanism. Right? So I'm looking right here. Remember, this is not correct. This is the correct one. So how did we get to this? You have to examine the step by step. We're being told this reaction occurs in two steps. In the first step, you have NO2 combining with itself to form NO3 and NO. NO is one of our final products. NO3 is not showing up in the final product, so I will just say this is the intermediate. It got made just to be killed, right? Intermediate. It got made here. It got used in the next step to produce NO2 and CO2. Also a product. Okay. We are told, they have to tell us. So you can't just guess from looking at the reaction mechanism, which is fast, which is slow. They have to tell you one way or another. They can tell you in words, this is slow. They can tell you this is the rate determining step. That's two different ways of telling you it is slow. Okay. One time I was at work and we're going to a meeting. It was three teachers, me, another chemistry teacher, and the physics teacher. The physics teacher is kind of slow. If you're taking physics instead of I don't tell her I said this, but she's slow. She takes too much time to get ready, and we're like, oh my goodness. I'm telling the chemistry teacher, should we just leave her? She said no, we're supposed to go together. And I'm like, oh, she is such a rate determining step. I know. And then she comes and she's like, what are you guys laughing at? I'm like, you are such an RDS. Ah. She's like, what? I'm like, you're a rate determining step. What? I'm like, don't forget about it. Let's go. And then we all went. I know. And so sometimes I'm like, no, I'm about to go in there and make her move faster. Okay, I need this whole ship moving. So I went there. I'm like, do you need help? What can we do to make you move faster? Because if we make you faster, we influence the overall reaction. She's looking at me like, what are you talking about? I'm like, you wouldn't understand. You wouldn't understand. I know. Anyway, yeah, that was her. So the first step is slow, the second one is faster, right? So once you examine the rate law of the second one, you can see once again, like we did before, it's the rate equal NO2, because since we have two NO2s is raised to the power 2, this should be power 2 over here, right? And then the second one is NO3CO. The rate law for the second one is fast. So this is, you want to know how to write the rate law for the elementary steps, but you want to know which one is significant in the overall rate, which is the first one. Okay, so what I like here is this picture. You want to once again know how to make sense of this picture. This one here, from my point of view, allows us to have some compassion. Yes, I said that word, compassion for the slow person. Okay, how do we have compassion for the slow person? They don't do this, but this would be a neat race if they were to have it. I did both track and cross country back in my days, but imagine if they had like a cross country race where people are running hills, but they're running hills and somebody runs a higher hill and somebody runs a smaller hill, right? So I'm like you, I am kind of the slowest person a little bit sometimes when it comes to running. Now imagine if this was one of those made up things I'm talking about, a made up race where someone starts here, but then somebody else starts here. And this first person has to get to where the second person is, and the second person has to get to down here, right? So we're trying to look at the chemical reactants and the kind of barriers they have to overcome. But since we're trying to look at this from a compassionate point of view to understand why one is smaller and one is bigger, or one is slower and one is faster, we're going to put ourselves in there. The first runner has a bigger barrier to overcome. They have to run up a really high hill, right? They have to run up all the way up here before they can run down here. The second one doesn't have that big of a barrier. They just have to go over here and then go down here. Okay? So between the two runners, the first one has a bigger barrier to overcome. The reactants here have a bigger activation energy barrier to overcome, so it takes them a little longer because they have to absorb energy and keep absorbing. Remember, they will not be able to get to this state here until they have met the requirement as far as energy is concerned. So they'll absorb energy. If they get to here, then they cool down, they're back to the beginning. Here, back to the beginning, back to the beginning, back to the beginning. Eventually they come up here and it's like, yay, then they become intermediate. So let's go ahead and label this because there's so many parts here. Remember, on the top of the hill, once they have reached the top of the activation energy barrier, they're called transition states. So you have TS1 over here, the first transition state, or the activation energy complex. That's what the chemical is called at the top of either hill. Transition state 1 here, transition state, I guess we can call this 2. Okay, so here we have reactant. Ultimately, we have product, right? So I would say the left side of each hill and the right side of each hill mark one step. So you see right here, it's not just the begin. It goes from here all the way to here marks one step. Okay, let me use a different color. When we go from here all the way to here marks the second step. So it's not just the top, it's like from the beginning to the end. Okay, so we have two steps. Step one, you can see, requires a lot of energy. It has a higher activation energy barrier. So what can we say about step one? Step one, the reactant forms, we can't really call it a product because it's not the end. We call what is formed here an intermediate. Okay, just because as soon as it forms what looks like a product, that product now becomes a reactant. So the chemical that looks like it's both a product and a reactant in the next step is essentially the intermediate. Okay, step one, what do you think step one is? Is it endothermic or exothermic? Just step one. Okay, yes, this is endothermic because it ends up at a higher energy level than it started, right? So it's definitely endothermic. And it's going uphill. Very good. As it goes uphill, it's gaining energy, but it lands right here. This step here is higher than when it started. Now the second step, step two, this one here is exothermic because it ends up at a lower energy than where it started, right? And not only that, it has a lower activation energy. So step two goes by a lot faster because there's less barrier for it to overcome, right? That's why between the two, step two is fast, step one is slow. It takes a long time to overcome a larger barrier. So hopefully you understand, you see some compassion for step one, and it kind of helps you understand. Sometimes people are slow because there's a lot of things they have to overcome, right? That's why we slow. Well, you can choose to look at it that way if energy is the goal. But from the point of view of the chemicals, endothermic is not very fulfilling because chemicals prefer low energy. People prefer higher energy. We want to have a high energy. We want to receive energy, right? People. Chemical chemicals, they actually are happier, they're more stable when they have lower energy. So for people, that what you're saying is true. For chemicals, the relationship is actually the opposite, right? So it's kind of like you have to relate people to chemicals, where in some cases the way I relate that, so I end up at the same point, is a peace of mind. Like the peace of mind is more stable, lower, less chaos. So for me to arrive at the same place where chemicals have a preference, I go with a peace of mind. The relationship where, things are just right, right. But if the goal, of course, is energy, yeah, endothermic, definitely more fun, definitely more fulfilling. Yeah. Sadly, that's not the personal goals or the elemental goals of the elements. They got their own goals. Interesting. So now we're looking at this one here, practice. We're getting close to the end. Nitrogen monoxide. Okay, so here we're looking at elementary steps. These are the mechanism. And we're told we have fast, fast, slow. Okay, hold on. For the reaction, find the overall balance equation, any reaction intermediates, the rate of the overall equation. Okay, so I'm going to do a lot, right? So what I'm going to do here, I'm actually going to start with the last one, rate of overall reaction. I'm going to start with this because I have to do a lot to write here. These are intermediate reactions. So the rate laws are pretty much just the rate of what I have here. Rate equal K, don't forget K, and O raised to the power 2. That's the first one. Rate, will I have space here? Equal K, H2, and 2O2. Ooh, barely made it. Third one, rate equal K H2O Oh, no, hold on. H2 N2O. Okay, so I wrote the rates of each so that here, rate of the overall, remember, rate of the overall reaction is rate of slowest reaction. So I can say here, rate equal KH2, the second reaction, right? N2O2. I'll write it right here. So since I've done this part here, I can erase this because it gave me what I wanted, the last one. Okay, reaction intermediates. I can figure that out as I'm balancing the equations. I'm going to be doing number 1 and number 2 together. So here, I have to add these reactions. I'm going to look, examine left and right and see what cancels out. I'm looking at 2NO. Let me use a different. Do I have NO anywhere else? No. I like to say that. No, I don't have NO anywhere else. But I do have N2O2 here and here. And I do see N2O, N2O. If they're on opposite sides of the equation, they cancel out. So this and this cancels out, this and this cancels out. Now these others I'm going to show here, they don't cancel out, they consolidate because they're on the same side of the equation. That consolidates, that consolidates, right? So I'll end up with 2NO. I'll leave the physical state so it doesn't get crowded down here. 2H2 to give me 2H2O plus N2. Yep. Okay. Oh, so I have to write the overall balance equation. I write on the side here. Can I write on the side? Can I? 2NO. Space is such an issue. 2H2. I think I might make it. 2H2O. Yep, looking good. And 2. Barely made it. Barely. Okay, that's my overall equation. What intermediates did I cancel out? I canceled out N2O2 and I canceled out N2O. Yay. I normally have to write this in a whole different page because I don't have room. But see, this became one of those areas where I was like, I really liked it. Because at first I hated it. And then I was like, wait a minute, I'm just not connecting with it. There's a difference between not understanding because it's above your head and not connecting. And I've realized for me, a lot of things, if it's not a recall question or somebody just spewing facts that I can't relate to, most of the time I'm just not connecting with the information. And if I'm not connecting it with it and I just don't care about it, you can explain it 100 different ways. I'm just like, okay, whatever. But once I connect with it, all of a sudden it's different, right? Then I care enough. More practice. Oh, so we end up with the catalyst right here. So we don't say a lot about the catalyst. So, oh, let me make sure I finish this part here. We do have more practice here. Once again, there is something missing. Should have been 2A. For this one here, the intermediate you can see will be a 2, right? Then when they say find the overall, identify all intermediates. Oh, rate determining step is the slowest one, RDS. Predict overall reaction, add these two, 2A plus B to give you A, 2B, cancel out the intermediates. And then the rate law that results from the following two-step mechanism. The rate law of the overall is the rate law of the first one, which is the smallest one, K, and then A raised to the power 2. These have to match. K, A raised to the power 2. The second one will be rate equal K, A sub 2, B, right? But it's the first one that affects the overall. Yeah, so see, that's not that bad. Then I think I answered everything, right? Okay, finally, catalysts. So your lab this weekend was about catalysts and how they work. So we kind of talk about catalysts very briefly. Here, catalysts are substances that affect the rate of the reaction without being consumed. So in the previous lesson we had before today, we essentially talked about a relationship between rate, and rate was represented by the rate constant versus temperature. And we saw how temperature, using the Arrhenius equation, affected the rate of the reaction, represented by K. Okay? And essentially, going back to the reaction energy profile, where we haven't spoken about that in reference to temperature. If you have a reaction like this, you have a reactant and you have a product, the role of temperature is this. Temperature does not do anything to the activation energy barrier. What temperature does is what a teacher does. My role. I am temperature in this analogy. What do? I encourage you, I teach, I present the materials in ways that are relatable so that you, as a reactant, can get to your desired goal, which is your product. Okay? So, what I do is influence your energy here through various legal means. I try my best, okay? I try. And what I do is help you to be activated enough so that you, right, can overcome the activation energy barrier, which can be a lot of things in life, right, to get to this level right here. And then you can get to your desired goal. And your desired goal is defined by you. And then you have satisfaction here, right? And that's my goal as temperature, to help you get to that activation energy barrier. Thank you. Okay, now this is what I will not do. Okay? You know, let me tell you the kind of things I faced as a young instructor. There was one semester, man, I'm just explaining this in front of the class, and I had some people say stuff to me, but you know what I focused on? I chose to focus on the fact that they understood the analogy well enough to tell me what they shouldn't have told me, okay? So here's what they told me after I explained the catalyst part. So this is what I will not do as an instructor. What the catalyst does, it says, catalysts work by providing an alternative mechanism for the reaction with a lower activation energy. I told them I would not do step number 2. What a catalyst does is, with the same starting point and same ending point, the catalyst lowers the barrier. Okay? So it lowers the barrier so that the reactants don't have to make it to that higher energy level, right? And then I'm like, and then they have the same end point. And then the student told me, well, why don't you just? And I'm like, excuse me? No, you still have to develop the mechanism to be able to overcome this activation energy barrier, because there are going to be future barriers that are even bigger than this barrier you face here. What are you going to do then? Right? Because the mechanism you use to overcome this barrier, you will have to build on that to overcome future barriers. If I lower this for you, you are happy, I'm not very happy. But then when you get here, then you're like, Professor White. And I'm like, I don't work in that school. Am I going to do that? And then I haven't done my job, right? My job really here is to help you build a mechanism, right? So I will not be a catalyst, not in this sense, not in this context. No, I will not lower the barrier. What I will do is encourage you guys to overcome the barrier on your own, and I will cheer you on at the end. I miss graduation, you know, like physical face-to-face graduation, because I'll stand there and high-five you on your way out if you graduate from the college. If not, I'll still high-five you in my heart. Yeah, but I will not provide a lower activation energy barrier alternative. No. But for chemistry, that's okay. It's okay. You're not defrauding the chemical, what you're doing, because you have to keep doing it all the time, and that's okay, right? The chemicals rely on you. But they do that. So as far as energy is concerned, that is the role of catalysts. So when do we need catalysts? Like in your body, if you're trying to make a chemical reaction in your body go faster, it's hard for your body to just raise the temperature. Sometimes your body raises temperature, but usually that's to fight infection, not to speed up a chemical reaction, right? But if your body wants to speed up a chemical reaction, what we have in our bodies are enzymes, and enzymes are biological catalysts, right? The biological versions of these catalysts. And so your body is able to employ the biological catalyst to do what they have to do to make reaction goes faster and keep you alive. But usually the temperature, employing a temperature, is the mechanism for your body to fight infection and other biological things that are going on. So we're told here, how do you identify a catalyst in a chemical reaction? You have to recognize that catalysts are the opposite of intermediates. They haven't said it here, but I'm writing this out to you so you can notice. Catalysts are opposite to intermediates. Okay, I gotta bring this in because people kind of vaguely remember stuff, and chemistry, you're not doing well if you vaguely remember stuff because you get confused. Catalysts are opposite to intermediates. So catalysts are consumed in an early mechanism step, then they are made later, meaning that, so let me try to break this down. How are intermediates different from catalysts? So say here, intermediate versus catalyst. Okay. Intermediates, if I can spell, are products first, reactants second. Okay, so this is the way I remember them, and this is how I identify them. So when I look at a chemical reaction and I see a chemical that appears for the first time as a product, and then I see the same chemical appearing in a different step as a reactant, I judge that chemical to be an intermediate, the one that was brought to the scene only to be consumed, or they get rid of it one way or another, right? That's the intermediate. The catalyst is the opposite. So the catalysts are reactant first, products second. And if we know the definition of catalyst, then this works, right? Catalysts are chemicals that are neither reactants nor products. They are consumed in the reaction though, and then they are reformed. Now, there's some people who just bypass all that and say there are chemicals in the reactions that are not really part of the reaction. That's actually not true. That's actually not true. They are consumed first and then they're produced second. But if you step back and look at it overall, it's like nothing ever happened to them. So some people who have an overview view of chemistry, they will present a catalyst like that. Because, you know, when I was in school, I memorized the overview definition of a catalyst. It's a chemical and a chemical reaction that is there to speed the reaction up, but it's never consumed. Then I got to organic and they said the catalyst got consumed. And I'm like, hold up a second. I learned it was never consumed. Like, yes, it gets reacted and it gets reformed. And I was like, oh, why can't you all teach us the truth in the beginning? You know? But it's just as your understanding gets deeper, then you're able to understand the nuances, right? And the details and the extra information. So I'm like, okay, whatever. Listen, I was that student. I was like you, okay? I had a comment for every comment that was given to me. But you know what? Even though I have students like that, I don't take it personal when they do that because I'm like, you have to be listening to have a if you are, even if it sounds like you're making commentaries to what I'm saying, that means you're listening. Because you cannot have a commentary if you're not paying attention. So I focus on that and I'm like, you know, at least you're listening. Which is what I want, right? At least you're listening. So yeah. Now that we see this, we're told that mechanism without catalyst, this one here, is very slow. When they have the mechanism with a catalyst, somehow it now splits into two steps. Excuse this part right here. They made the slides accessible and then introduced all these little characters. I don't know where they got them from, but I can't change that because they're pictures. So now we're looking at this. Our focus is a mechanism with catalyst. Look, we have, I'm examining this. I see Cl, okay. I see Cl here as a reactant, Cl as a product, right? And then I see, do I see something else here? O3, O3, O2, ClO as the product, then ClO as a reactant. So Cl is a catalyst, right? Because it's a reactant first, then it's the product. And then ClO is an intermediate. Why? What is its role first? It's first a product, then it's a reactant. So the order in which you see the chemical appear determines what the role is in the chemical reaction. I mean, yeah, here this is fast, this is slow, but remember, it's easier to come to that conclusion when they have all these titles for you, right? In your homework or on the exam, yeah, this could be on the exam. They won't have all those words to help you out. So you want to remember the order you saw them. Intermediates, they're products first, reactants second. Catalysts are reactants first, and then products second. Okay, very close to the end. So remember, I already talked about this, how catalysts provide the alternative pathway. Sometimes in the process of providing the alternative pathway, they split what used to be a one-way reaction into a two-step reaction, because that's how they're able, the catalyst, to influence the mechanism. That's fine. I want to talk about, here, catalysts are substances that affect the speed of a reaction without being consumed. Just means that they get to be recreated when the reaction is over. Here, we have homogeneous and heterogeneous catalysts. Homogeneous just means the catalyst you're using has the same phase as the reactant. If the reactants are gases, say H2 and O2, the catalyst also has to be a gas. Whatever it is, let's say X, it has to be a gas, right? That will be a homogeneous. Heterogeneous catalyst, the catalyst is a different phase with the reactant, so it may be a metal when the reactants are gases. Okay, so you want to be aware of those terminology. Then finally, how these gases work, or how the catalyst works. Let's see. Oh, that picture is still here. So homogeneous, once again, same phase, catalyst and reactants right here. Here, the catalyst has a different phase. Most likely here, this is a solid based on how the atomic structure looks. This one here is showing you the catalyst working as a matchmaker. I like this one here because it ends on a nice note, a story, right? Catalysts, you can see right here, this is a heterogeneous situation. So the catalyst, this is a heterogeneous catalyst in operation. The purple part is the catalyst, and then the top part is the reaction. So what the catalyst is acting as here, it says so right here, it's a matchmaker. So this to me is more like speed dating. Okay, that's how I can relate it to life. From what I've seen on TV, this is more like speed dating. So what the catalyst is doing is providing an avenue, a place for the reactants to meet. Now the reactants without the catalyst will be in the container. Most likely these are gases, right? From what we see here. They could also be liquid. But based on the shadow they leave as they move, it looks like a gas. Okay? And hydrogen is a gas. So you have a hydrogen molecule here about to react with ethene. So ethene is going to be CH2 double bond CH2. Okay? They would react without the catalyst. It would just take them longer to meet. So the catalyst is providing the avenue for them to meet, like a speed dating scenario. The catalyst has to have an affinity for each reactant. So each reactant has to somewhat be drawn to the catalyst. That's what happens here as they are adsorbing on the surface of the catalyst. They're drawn to the catalyst. When they get to the catalyst, while they're still drawn to the catalyst surface, they start moving around. So you can see here what's happening, okay? You can tell I'm smiling. This is kind of moving around like, hey, like, ooh, I see what I like right here. Okay? They have an affinity for the catalyst, but they're also drawn to each other as reactants. So as the molecules are kind of sliding, diffusing on the surface of the catalyst, they find each other. So here, they find each other. Hey, they meet. Then what happens? That was quick. They react with each other. And when they react, so you see how we had 1, 2, 3, 4. They move around, they react. Now we're left with 1, 2. Because one reacts here, this is a new one attached. The other one reacts here, this one attaches too. So this ethene molecule essentially took in two hydrogens. Yes, they both want to go there because if they don't want to go onto the catalyst surface, the catalyst is not going to be a matchmaker. Right. If they want to just find each other on the side, there's no need for the catalyst. So now they react, a product is formed. Now the product does not have a high affinity for the catalyst like the reactant did. See, this is so important. If you are an engineer, a chemical engineer designing catalysts, you kind of have to think about that. You don't want the product to sit here because this is a ground for future reactants to come and meet. You want that seat empty. If y'all found each other, move. Let there be room for those who want to find another reactant. So once the product is formed, you want the product gone. So desorption take place and the product leaves, leaving behind reactants looking for the other reactants. Very important job of the catalyst, right? Now, this is such deep stuff. I like the deep stuff. In the container, all you see is nothing. No, I shouldn't say that. If you're in the lab, it doesn't sound as exciting as this. You just see, chemical changes. If there's a chemical change, if there's a color change, you see it. If there's no color change, you're just in there looking at stuff happening, It's like, yeah. Are they bubbles? Not really sure. Oh, it changed pink. It's the end. But when it comes to the mechanism, this is what's going on. It's like a lot of movement. Yeah. Molecules coming in, meeting together, leaving together, new ones coming in, kind of like a production line, but of products. Right. So once the products form, it's important for the product to not linger on the catalyst surface because the catalyst surface makes a difference in how many products it can produce, right? Yeah. So yeah, essentially this is what happens right here. And that's the end as far as this is concerned. You get new reactants and the process starts over and over again. So your lab that relates to this has to do with the behavior of catalysts. Now, I may go more into how the pH influences the catalyst, the temperature, and things like that. But once again, this is pretty much what we're going to cover about catalysts. So, yeah, this is the end of the chapter. Some people hate this chapter. I'm like, what are you talking about? You need to just connect with it. I think it's an interesting chapter. Maybe I overly
informal young people.
I think it's an interesting chapter too.
Oh, okay, you wanna know what happened? I didn't realize my headphones were sitting next to me and they were on. I started hearing sounds and I'm like, where is the sound coming
Sorry, that's the background sounds. I think it's an interesting chapter too.
Okay, I'm glad you enjoyed it. No, I didn't have my headphones on. They're sitting next to me, but they're still on. But it was loud enough to where I could hear you talking. Okay, but this is all I have for today. I've already gone over 15 minutes, so.
Okay, thank you. You made it really
you're
fun for
welcome.
me to be able to understand. Usually I just watch the recordings and I get really sad because I can't really speak like in the chat. I don't get to speak to you and just like talk to you.
Oh,
Yeah.
okay. Well, you should show up. I really enjoy this too.
Yeah. It's
Okay.
usually because I have a class at this time. The background noise that you just heard is just my other class. I'm not really paying attention to the other class. So like I'm at two classes at once. But yeah.
I see. Okay. Okay, well, thank you for showing up.
No problem. Thank you. It was really fun.
Okay, bye.
Bye-bye.
Okay, thank you. Yeah, if you have any questions, you can go ahead and send me email or something like that.
Okay. Thank you. Have a great day.
Okay. Thanks, you too. Bye. This is so funny.